Hey folks, so in this video we'll be looking at the example of an airplane moving down a runway. So the problem says an airplane starting from rest, so we're going to highlight starting from rest since that's important information, accelerates down a 1,721 meter long runway for 32.8 seconds. We're also going to highlight those two pieces of information since those are also important. Determine the acceleration of the airplane and the takeoff speed. So those are the two quantities that we are looking for, and we'll highlight those. So the first step in solving a problem is to define your coordinate system. So I'm going to choose to have the positive x direction be to the right. That's just my choice. You can choose whatever you want. You can choose it to be left. You just need to stay consistent when you define what your known variables are so that they're consistent with your coordinate system. This is a one-dimensional kinematics problem, which is 2.5. Now that we define our coordinate system, our next step is to draw a motion diagram. We're told that we're starting from rest, but that it's accelerating down a runway. So the acceleration and the velocity are going to be in the same direction, to the right, so we know that the airplane's going to be speeding up. For an object speeding up, we know the motion diagram should have an increased spacing between the dots to reflect that speeding up. So that's what we have here. We have an object starting from rest and it's speeding up. Now I'm going to mark this first dot as green, and that's going to be our initial position, and our last dot, or our final position, as orange. So now we're going to start filling in our known and unknown variables. So at our initial position, we're just going to call this 0 meters. Now that's arbitrary what you call it, but it just makes the math easier if we just call that our origin of 0 meters. We're told that the airplane starts from rest, so the initial velocity is going to be 0 meters per second. Now at this final position, we know that it's taking off at the end of the runway, which is 1,721 meters. So that's our final position. We don't know anything about the final velocity because that is related to what we are trying to find. Spanning the entire motion diagram, we know a few pieces of information. The time that it takes for this motion and the acceleration is 32.8 seconds. The acceleration we don't know anything about, but we are asked to solve for it. So now that we've filled in all of the given and unknown information, and we've got a picture of what's going on here physically, we can confirm what it is we're actually trying to find. So we're trying to find the acceleration of the airplane, and we want to know what is the takeoff speed right before liftoff. So the acceleration is going to be to the right, so we expect that to be positive and have units of meters per second squared. And then we're asked for the takeoff speed. Now, just a word of caution, the takeoff speed and the final velocity are not the same thing. The speed is a scalar, while the final velocity is a vector. So to get the speed from the final velocity, we need to take the magnitude of the final velocity, and that will always be positive, and it's going to have units of meters per second. So now we've visualized the whole problem. We know what we're looking for. We can take a look at the kinematics equations to plan our solution, which is our next step in the problem-solving framework. So looking up top here at our kinematics equations, we want to look at what our knowns are and what it is we're trying to solve when choosing these equations. So we know what the position initial and the position final is, And we know what the initial velocity is. We also know the time that all this motion is happening over. So looking at our equations, the equation that fits the bill to solve for the acceleration is the position as a function of time equation. And so that equation is the final position is equal to the initial position plus the initial velocity multiplied by time plus 1/2 times the acceleration multiplied by time squared. We know the initial and final position, we know the initial velocity, we know the time, we are solving for acceleration, and we know the time. So we have one equation, one unknown, we can solve for it. So now we need another equation to solve for the final velocity. Looking up at our kinematics equations, we've got two equations that are in terms of the final velocity, but they also are in terms of the acceleration. So there's two unknowns there. But after we solve for the acceleration in the first equation, we'll just be left with the final velocity as the only unknown. So it really doesn't matter which equation you choose, because we know all the information in both after we solve for acceleration. So I'm going to choose the velocity as a function of time so I don't have to deal with taking squares or square roots. So that equation is the final velocity is equal to the initial velocity plus the acceleration multiplied by time. We know the initial velocity, we are going to solve for the acceleration, and we know the time, and we are solving for the final velocity. So we have one equation, and eventually we're going to have one unknown. We can solve for it. Overall, we have two unknowns and two equations, so we are capable of solving for both. So starting with the first equation, we have the final position is equal to the initial position plus the velocity initial multiplied by time plus 1/2 times the acceleration multiplied by time squared. We can plug everything in that we know, which is 1,721 meters for the final position, 0 meters for the initial position, 0 meters per second for the initial velocity, multiplied by time, because that's just going to be 0, plus 1/2 times the acceleration, which is what we're looking for, and then time, which we know is 32.8 seconds, and that's squared. First term 0, second term's going to be 0. Now we can just get acceleration by itself. And so we have 1,721 meters multiplied by 2 divided by 32.8 seconds squared. Plugging that into your calculator, you'll find an acceleration of 3.20 meters per second squared. So that is our answer to the first part. Now that we've solved for the acceleration, we can move to the second part of finding the final velocity. We're going to start by using the second equation. So we have the final velocity is equal to the initial velocity plus the acceleration times time. We have the final velocity is equal to 0 meters per second plus the acceleration we just found, 3.20 meters per second squared, multiplied by time, which is 3.32.8 seconds. Canceling out units, we have seconds up top, and we'll get rid of a second on the bottom. And then plugging that into your calculator, you find that the final velocity is equal to 105 meters per second. Again, we were asked to find the final speed, or the takeoff speed, And that's not necessarily going to be equal to the final velocity. So we need to take the magnitude to get the final speed. So the magnitude of the final velocity is also equal to 105 meters per second. Now, if our final velocity was negative, then that velocity and the speed will not be the same value. And so that's something you're going to have to watch as you go through these problems is the problem asking for the velocity or is it asking for speed? So let's go through. Our solution is complete. We found both quantities. Is the sign of the answer correct? Both positive as expected. Does the answer have correct units? Speed is meters per second. Acceleration is meters per second squared. We're good there. Is the magnitude of your answer reasonable? Well, 105 meters per second is roughly 250 miles per hour. And that seems reasonable for a small plane to be able to take off. So we'll check that off.